Hey there, AppSec engineers. Welcome back to this video series on application security. I'm Ganga, and I'll be walking you through the specific example of stored XSS in Node.js applications. We shall be looking at both the attack as well as the defense section today. Did you know that in May 2024, Cisco, the networking giant, had issued a security advisory detailing multiple vulnerabilities in Cisco's Finesse web-based management interface? The vulnerabilities in question involve a remote file inclusion vulnerability and a server-side request forgery attack. Specifically, the stored XSS could be executed by exploiting the RFI vulnerability, while the SSRF attack could be conducted on affected systems through the web-based management interface. But what is XSS and what is stored XSS specifically? Stored XSS or cross-site scripting occurs when an application stores malicious JavaScript code in its database. When other users view the stored data, their browsers execute the malicious code. In our example expense management system, this happens when an attacker submits an expense with malicious code in the text fields. Managers viewing the expense list unknowingly execute the stored malicious code. Therefore, sensitive data like authentication tokens can get stolen. Well, for one, you could have session hijacking, you could have token theft, data exfiltration, and even privilege escalation. And on the business impact of things, you could have unauthorized access to financial systems, fraudulent expense approvals, compliance violations, and potential audit failures. Enough talk. Let's take a look at this example application and find out what is wrong with it. Before diving into the attack section, let us take a look at what is wrong with the application code itself. Our expense management application has several controllers. One of them is the expense controller. It contains several methods such as create expense, update expense, approve expense, so on and so forth. In this case, the create expense method is vulnerable in several ways. On lines numbered 27 through 29, directly from the request body, without any validation, sanitization, etc. So number one, you have direct storage of unvalidated user input. Looking at our code, we are taking user input directly from the request body and storing it in our database. See how request body name, request body reason, and request body merchant flow straight into our expense create method. This means any malicious script tags, event handlers, or JavaScript code gets stored exactly as submitted. Secondly, there's no sanitization of HTML or JavaScript content. We are missing the very crucial security layer of input sanitization, which means when a user submits something like script alert hacked, so on and so forth, if a user were to submit JavaScript code directly, it would be stored as raw HTML or JavaScript directly in our database. And therefore, the next person that were to execute this data, it would execute on the user's browser. You will also notice that we do not have any sort of content security policies. These headers are simply not set, and most modern browsers would require that you have something of this sort. Without a CSP configuration, we are not telling the browser which script should be executed and where they should be sourced from. There is no whitelisting or blacklisting going on here. Finally, there is no validation for the user input data. While we do validate the user's authentication token, we are making a dangerous assumption that an authenticated user will only submit safe data. Let's go ahead and perform an attack to showcase how this could work. To begin with, I will log in as a normal user. Let me set the token using this value. And now if I were to echo this token, I will see it's a JWT representing this session. And now for something a little curious. So you will notice that what I've done here is construct a payload. And the important settings here are really that I'm using this lower authorized user to create a new expense, which is in this case an RSA conference with a certain project ID, and the merchant is named SLV. In the reason block, I'm inserting a straight JavaScript command. And because I know that the application is going to store this just as is, I should be able to perform stored XSS, and this would mean that the authentication token would be visible from the local storage of whoever comes later. Let me post this request. And you will see that the expense so-and-so has been saved successfully. Let's go ahead and look at the application and see how this would show up. In the application itself, I have the RSA conference expenses section. And there are several expenses listed here. One of them reads RSA conference with an amount of 20. There is the merchant SLV and it's waiting for approval. However, if I were to look at the reason, you will notice that the JWT token associated with the manager's account in this case is going to be visible directly. Only because the script used while posting this was specifically only trying to show a pop-up message is it like this. It is also very conceivable that this could be shipped somewhere else and therefore session hijacking can happen very realistically. Now let's talk about the defense against something like this. Clearly a lot of this is occurring because we're taking inputs directly from the users and ingesting it into our application, and in this case, saving it directly to the database. What are some potential ways we could stop something like this? The first solution against something like this could be using input sanitization. There is a very well-known library called DomPurify that allows you to create a first line of defense by cleansing the user input before it reaches our database. When a user submits an expense, DomPurify strips out dangerous HTML tags and attributes. It converts potentially executable content into safe text, and it also preserves legitimate formatting while removing scripts. For example, if you have script alert something, this would become harmless text rather than staying as executable code. Here's a side-by-side comparison of what we're trying to achieve. From the DomPurify library, we're able to leverage the sanitize method to take a look at our name, reason, and merchant fields, and we're able to sanitize the user input before passing it to our database. This acts as a first line of defense against any potential malicious inputs. Always remember that defense is a layered approach. Other strategies here would involve using content security policy. CSP is a browser-level defense that controls what code can actually execute. By setting default source to self, we are ensuring that only scripts from within our own domain can run. Further, inline scripts are blocked by default, and external script sources must be explicitly allowed. Think of it as an allow list for JavaScript execution in your application. The next possible solution is to use HTTP-only cookies. HTTP-only cookies provide a final layer of defense by making sensitive data like authentication tokens inaccessible to JavaScript. Cookies, marked as HTTP-only, can't be read by client-side scripts. Even if an attacker injects malicious code, they can't steal the cookie. Combined with secure and same site, this creates a secure token storage solution.